All right, we're going to introduce the directional derivative today. And the directional derivative is going to lead us into a very important concept that that's going to be very important for the rest of the semester. So we've said before that the partial derivatives of a multivariable function tell us about the rate of change of the function value. So if we have z equals f of x, y, we get the rate of change of z in the direction of the x-axis for a specific value of y, so in the x direction for a specific value of y, or in the y direction for a specific value of x. What we're interested in today is finding the rate of change of that function in any arbitrary direction. So not just in the x direction, not just in the y direction, in any direction. So to start, we want to find the rate of change of z equals f of x, y in the direction of an arbitrary unit vector. So we're going to say our unit vector u is, and I want to stress that we're talking about a unit vector. U is the vector AB in component form. So vector in the plane, going in some direction, and we're saying the magnitude of u is 1, and we're talking about vectors again, so thankfully we're back with our beloved Tranya. So, and we're interested in this at a point x0, y0. So we're at some point on a surface and we're moving in some arbitrary direction. We want to know how the function value, how the height of our surface, if we think of z as height, is changing as we move in the direction of that unit vector. So let's draw a picture. Here are our axes. And our generic surface up here. And here is our point x0, y0 in the xy plane. And we're going to project that up onto the surface. So there's our function value f of x0, y0. And we're going to say this surface is given by z equals f of x, y. And we want to move in the direction of some vector I'll call PQ. So there's PQ. So we're moving along that direction. And we're moving to point Q, which is some point x, y. So I'm going to project that up onto our surface. So on the surface, we move along some curve. And this is going to be at point f of x, y. We want to know how does the function value change from x0, y0 to xy as we move along in this direction, PQ. So PQ is, I'm going to define a unit vector down here in the plane. There is going to be, I'm going to make it thick here. There's my unit vector u. So that vector is u. So PQ is in the direction of u. U is a unit vector. So there's our picture. All right, our average rate of change with respect to the distance traveled in the direction of u, is going to be given by, average rate of change is relatively easy to calculate. F of xy, we're just going to calculate the change in the function, minus f of x0, y0, and we're going to divide by the magnitude of PQ. So that's going to be the average change in our function value with respect to the distance we move along PQ. And we're interested in an instantaneous rate of change. Our directional derivative is going to be an instantaneous rate of change. So we're going to take a limit. So that instantaneous rate of change will be given by the limit as the magnitude of PQ approaches 0 of that average rate of change, f of xy minus f of x0, y0, divided by the magnitude of PQ. This limit is called the directional derivative. So that's the directional derivative of f at x0, y0 in the direction of u. Because PQ is in the direction of the unit vector u. So we call this limit the directional derivative of f at a particular point in the direction of this unit vector. It gives us the rate of change of our function. If our function z is the height, the rate of change in our height, our altitude, as we move in the direction of unit vector u. For each unit that we move in the direction of u, how much does our altitude change? How much does our height change as we move along that direction? And we write d sub u of f of x0, y0. Now, one thing I want to point out here is we're talking about the rate of change with respect to the distance that we travel in the direction of u. We are parameterizing in terms of arc length. We're parameterizing in terms of a distance we're traveling along a unit vector. So what we're doing here is we're parameterizing our derivative function in terms of the arc length. So I talked about how parameterizing in terms of arc length is going to be an important concept. This is an example of us parameterizing something in terms of arc length. All right, we need a way to calculate this quantity. So that's our next question, how to calculate. So just like we don't, in Calc 1, we didn't want to have to use our limit definition of the derivative to calculate the derivative every time. We wanted a more convenient way. Same thing with our multivariable derivatives. We don't want to have to use that limit every time. We want an easier way to calculate this. All right, so let's go through that procedure. How do we calculate this directional derivative? PQ is parallel to u. So we can say that PQ equals HU for some scalar h. Vectors are parallel if they're scalar multiples of each other. And we said that u, our unit vector, we were going to say is the vector AB in component form. So PQ is HA, HB. And now we can say that x, the arbitrary point that we end up at, the x component of the x coordinate of that point, after we travel some distance in the direction of u, is x0 plus HA, and y is going to be y0 plus HB. The distance that we travel along PQ in the direction of u is h. So we're taking advantage of this fact that we're parameterizing in terms of the arc length. So the distance we travel along PQ in the direction of h, in the direction of u, is h. So we can write the limit as the magnitude of PQ approaches 0, this directional derivative, our definition of our directional derivative. We can rewrite, so here's our original expression, limit as that magnitude of PQ approaches 0 is the limit as h approaches 0, the distance we travel along that vector approaches 0, of f of x0 plus HA, comma, y0 plus HB, minus f of xy, or x0, y0, sorry, over h. This is how we're going to define the directional derivative. So we said the limit, this limit was the directional derivative. Well, we're going to define our directional derivative as this limit. Because now we have this, we're parameterized in terms of our arc length. We can deal with it, we can deal with this limit much more easily than this limit. This limit has to do, our limit has to do with magnitude of a vector. This limit, we just have a scalar here that we're dealing with. So this is our definition of our directional derivative. And I'm going to say of f at this point x0, y0 in the direction of u. These two limits are equivalent, but this is what we're going to take as our definition because this is going to be easier for us to work with. It might not seem like we're closer to coming up with a way to calculate this, but we are. So you have to trust me for a second. All right, I want to make a couple of points. So this is our definition of our directional derivative. If u, our unit vector, is I hat or j hat, so we're moving in the direction of the x-axis or in the direction of the y-axis, our formula reduces to the definition of the partial derivative. So I'm going to say the directional derivative becomes the usual partial derivatives. Of f. And that's good because the partial derivative is just the directional derivative in the direction of x, in the direction of I hat, or the partial derivative in the direction of j hat. So we would hope that our definition of this directional derivative in arbitrary direction becomes the same as our regular partial derivative in the direction of our coordinate axes. So the partial derivatives are actually a special case of directional derivatives. All right, so with that limit, we still need a way to calculate these conveniently. Well, we're going to do that using the chain rule. So right now we have, with our parameterization, we have f of xy where x equals x0 plus HA and y equals y0 plus HB. So f is implicitly a function of h. So we're going to use the chain rule. The derivative of f with respect to h, which is what we want. How does our function change as h changes, as the distance we travel in the direction of that unit vector approaches 0, is going to be the partial of f with respect to x times dx dh plus the partial derivative of f with respect to y times dy dh. That's going to give us our derivative. And I can rewrite this just in a slightly different form. I'm going to write it as f sub x at xy. Well, dx dh is just a plus, and I'm going to write f sub y at our particular point xy. And dy dh is just b. And at x0, y0, the point that we're at, the point xy that we're at, we're taking the limit as h approaches 0. So our point xy is getting closer and closer to x0, y0. So in the limit, so I'm going to say h is approaching 0. And I can also say, in parentheses, the limit as h approaches 0. So here I'll say, sorry, my board just died. Give me just a second. All right, got it plugged in. It'll be back up and running in just a second. Okay, so we're going to say h equals 0. At the point x0, y0, h equals 0. We're taking the limit as h approaches 0, so xy is getting closer and closer to x0, y0. Limit as h approaches 0. This is the instantaneous rate of change. Our directional derivative becomes df dh, the rate of change with respect to h. When we're moving along that in the direction of that unit vector is the other notation, our directional derivative notation, the derivative in the direction of u of f at x0, y0 is the partial derivative of f with respect to x at x0, y0 times the x component of our unit vector plus the partial derivative with respect to y at our point x0, y0 times the y component of our unit vector. And this is going to be the formula that we will use to calculate the directional derivative. All right, so we've come up with a way to find the rate of change of our function. If our function represents height, the rate of change in our height, our altitude, as we move along in an arbitrary direction, in the direction of an arbitrary unit vector, this is how we're going to do it. The rate of change of our function with respect to x times the x component of our unit vector plus the rate of change of our function with respect to y times the y component of our unit vector. And what I want us to think about, what I want everyone to think about before class next time is, what does this look like? We have something derivative with respect to x, something that has to do with the x part of our function times the x component of a vector plus something that has to do with the y part of our function times the y component of a vector. So what does that look like? When we will make that more explicit in class, and we will take advantage of what that actually looks like. Now, I'm going to stop in just a second. This is where I wanted to get how we're going to calculate our directional derivative. This concept of the directional derivative is going to be very important. This quantity that we have here we're going to use in ways that you can't imagine right now. It's going to give us a lot of useful information. But I want to make a note, if we can, if our unit vector, if we define our unit vector u, if our unit vector makes some angle theta with the positive x-axis, then we can write u, our unit vector, is going to be cosine theta I hat plus sine theta j hat. And our directional derivative, just a slightly different form for our directional derivative of f of xy, is going to be given by the partial derivative with respect to x cosine theta, x component of our unit vector, plus f sub y sine theta. So just another, if we define our unit vector in terms of the angle it makes with the positive x-axis, this is the form that our directional derivative is going to take. I also want to emphasize we can find an infinite number of directional derivatives in the direction of any arbitrary unit vector. So there are an infinite number of directional derivatives. And again, the directional derivative represents the rate of change of our function with respect to the distance that we travel in the direction of a unit vector. So if we say that our function z represents height, the directional derivative tells us the rate of change of our height with respect to every unit that we move in the direction of a particular vector. So for example, I could say my height is changing by 3 feet for every foot that I move in the direction of that unit vector. All right, we'll do more work with this in class.